All right, well, good afternoon. Today I'm going to talk about some new instrumentation that we've been adding to the Open vSwitch with a primary goal to improve visibility into virtual networking. And it actually touches on a number of subjects that we've already talked about this morning. So we'll be using a demonstration using OVN and Docker containers and Genève to create the tunnels. I'd like to start by sort of stepping back and looking at what the role of instrumentation is in an SDN environment. And I really like this slide from Broadcom. And it's really saying, you know, you have this instrumentation in your data plane. And what you want to do is have that telemetry stream to some kind of analytics software which feeds metrics into your orchestration systems, which can then in turn improve and optimize the performance of the system you're managing. And last year I gave a talk specifically about feedback control and SFlow, but I'd like to just sort of touch on a couple of the points that I raised then. The first is that SFlow is an industry standard that's supported by most of the merchant silicon vendors, in particular Broadcom on the previous slide. And so it's in pretty much every data center switch you can buy these days. It's also been in Open vSwitch since before version 1, which gives you visibility into the virtual edge. And it also it has two primary methods of instrumentation. The first is to periodically export standard blocks of counters. So each SFlow agent within the infrastructure will be sending out counters on a polling schedule. And the other is asynchronous export of randomly sampled packets. And I'm going to give two examples of additions that we've committed relating to each of those. So the first set of changes relate to counter metrics that have been added to Open vSwitch. Have I lost the... Hello? Testing? Okay. Chad Norgan of Rackspace last year gave a really interesting talk about some of the operational considerations of managing a large fleet of Open vSwitch instances. And so some of the counters that he suggested have been added to the SFlow export, and they get exported along with all the other counters, such as interface counters. So the key areas are visibility into the CPU utilization of Open vSwitch, and the other is how effectively the data path cache is working. So what's your cache hit rate? And both of those metrics are really useful to manage to ensure that you're getting optimal performance. The other area that's interesting is SFlow's packet sampling mechanism. And when a packet sample is taken, it's not just the packet header that's exported. It's also used to probe the forwarding state associated with how that packet is being treated. And so a patch has been submitted to and actually accepted in the Linux kernel that it's a little more than one line. But I think this captures the essence of it, is instead of just passing up the packet header in the up call from the data plane, we also get the full set of actions that were applied to that specific packet. And that has a number of advantages. Firstly, it's future-proof, that all actions defined today and in the future will now be visible to user space. And it's also, and you're no longer limited by how much data you can encode in a cookie when you add the rule to the kernel. And the other thing is it's completely accurate, that you now have, you've fused together the actions and the packet that they were applied to in the data plane, and so you can rely on them in the user space in order to analyze how packets are being forwarded. So this next slide comes from the SFlow specification as to how tunnels are reported. And really it focuses on the ends of the tunnels, so the encap devices and the decap devices, and those are typically Open vSwitch, and so these structures can be populated by Open vSwitch as it encapsulates and decapsulates packets on various tunnels. And I think the easiest way to sort of understand how that works is through an example. So basically what's going to happen is the actions are going to come up with the packet header. The user space agent has now been enhanced to parse those actions and populate the SFlow structures. And this is what it looks like. This is a decoded SFlow datagram using the open source SFlow tool. It's basically a command line SFlow pretty printer. And so if you're doing anything with SFlow, I'd recommend you have it in your toolbox, since it's a very good diagnostic tool. But what you can see is you have the packet header at the top there. You can see the size of the packet before sampling, and you can see the first 128 bytes of the packet. They're dumped in hex there. And then there's additional metadata that's being attached to that packet. So you get to see the virtual network identifier. It's reported as an ingress identifier, so you know that that was the tunnel that the packet arrived on. And then you also have the metadata describing the tunnel. So the MAC address, the IP addresses and the UDP sockets that handle that packet. So I think the best way to sort of show how all these pieces come together is through an example. And so this is a test bench that we set up. It's trying to capture all the basic elements of a realistic deployment. So it's built on VirtualBox, and we're using Cumulus VX virtual machines to simulate the physical leaf and spine network. And Cumulus VX is basically a VM version of Cumulus Linux that would run on an open vSwitch, on a physical switch. And we've set up BGP to set up ECMP leaf and spine forwarding there. Okay, is that coming through? Okay, sounds a little bit better. So that's representing the physical network there. You've got an ECMP leaf and spine network, and then we've attached two servers, each of which has open vSwitch and a pair of Docker containers. And then there's the OVN daemon running on each of those servers. And we've also installed the host SFlow agents that report on the CPU metrics for both the containers and the hypervisor. And on the right, you can see the orchestration system server that's been connected through an out-of-band management network. And we've created two logical switches. One connects the rightmost containers, and the other connects the leftmost containers. And then we're also streaming the SFlow data to the same server, and we're driving a real-time dashboard, which I'm going to demonstrate. So this demo is available on GitHub. Anybody can download it and replay it. Basically, it's driven off a PCAP packet capture of all the SFlow from all these different data sources. And I'll just run it here. So let me just walk through. Oh. Sorry. All right, let me walk through the different charts. On the left side of the dashboard, you can see a sort of a depiction of the setup that we just showed. We have the leaf and spine network at the bottom. We have the servers in the middle, and then we have the OVN logical networks at the top. And what you can see is the two logical networks, and the dotted lines represent the logical connections between the Docker containers and their respective switches. And you can see the line intensities changing as traffic flows along those logical links. And below, you can see the actual, in solid lines, the actual physical path that those flows take across the infrastructure, going through the vSwitch, through leaf 1, through spine 1, leaf 2, to the second open vSwitch where it's decapsulated and delivered to the destination container. You can see as we're running a pair of iPerf sessions between the pairs of containers, and so you can see the traffic flow between one pair and then flow between the other, and occasionally you'll see the path through the physical network go magenta, and that's when those links are shared between multiple logical networks. Working down the strip charts along the right of the diagram, the top one shows you the CPU utilization of each of the containers. The one below that is actually joining data from multiple sources. So it's taking metadata about the Docker instances and merging it with traffic data that it's getting from the Open vSwitch instances. And so it's giving you traffic flows between containers. And then the diagram in the middle shows you the OVN view of the world. So it's showing you the logical switches, the MAC addresses associated with the logical switch ports, and then the IP pair flows as they traverse those logical switches. And then below that, we get the performance metrics from Open vSwitch itself. So the data path miss rate and the CPU utilization of the Open vSwitch instances. And then right at the bottom, we get the view that the physical network sees. So what we see are the actual outer tunnel layer. So those are those outer IP addresses. And then you can see the VNI, and then the inner MAC addresses and inner IP addresses. And all of this information is just decoded out of those first 128 bytes of the packet that the switches are reporting. So they don't understand this at all. This is all analytics that are done at the receiving end. And so this kind of gives you an idea that you have a pretty comprehensive view of all the layers and all the interactions in this entire setup. And this isn't an exhaustive list. I've just picked up some representative metrics. There are hundreds of possible metrics you could be plotting here. And depending on what your operational requirements are, you might pick different ones. The fourth one is the Open vSwitch metrics. So those ones that I described earlier that Rackspace had identified. So it's the CPU utilization of the Open vSwitch user space, and then the data path miss rate. So you can see that the miss rate is well under 0.5%. So not many packets are making it up to user space. So this next slide is just to try and convince you that this actually scales beyond one little VirtualBox simulation. Right now, the supercomputing show is running in Austin, and we set up a real-time dashboard that's collecting data from these 100 gigabit switches and displaying them in real time. So if you connect to that link, it's basically a dashboard just like the one I showed you, showing flows through this small simulation. And now we're seeing what a dashboard might look like on a real network. And actually, dashboards like this are an important use case for this kind of real-time analytics. It's sort of representative of the general sort of DevOps use case where you want to provide information to operators. And I sort of see this as the sort of the slow path in a control loop. You know, you have human beings who are looking to allocate resources differently or understand how their applications operate in production so that they can improve the performance of them. But what I think is the more interesting use cases are actually when you close the loop automatically. And so what the slide is trying to show is that the elements that you're orchestrating are all becoming sort of commodities. You have commodity x86 servers, you have commodity switches, and that really the value you add is in how well you can manage those resources, and that analytics built into that infrastructure can be used to drive controls into orchestration systems in order to improve performance. And I'd like to go through an example that we demonstrated the Open Networking Summit this summer. And this was looking at how to load balance large flows across an ECMP fabric. And in this case, what we're doing is detecting when a link is carrying more than one large flow. Because if you can see to the left of the strip chart, those gold regions are areas where flows are interfering with each other and competing for bandwidth across a path. And so the throughput is half what it should be. When you activate the controller, it detects that situation, and then it pushes a traffic engineering source routing control to the ingress top of rack switch, which steers that traffic over an alternative path. In ECMP fabrics, there are a lot of parallel paths, but unfortunately, hash-based load balancing isn't terrifically successful in load balancing these large flows. And so being able to rapidly detect and ameliorate these situations can really help in terms of throughput. What's interesting about this as well is we're using segment routing as the technology for routing traffic across this network. And I won't go into great detail on how that works, but it's basically using MPLS And it's a source routing technology, so you can actually push policy-based routes. And you can see at the top right there is an example. You sort of have a 5-tuple for a TCP flow, and then you have a set of MPLS labels, and those correspond to labels assigned to those switches. And so it allows you to specify a specific path that traffic is going to take across that backbone. And what's interesting about it is actually Open vSwitch can push MPLS labels. And so given this visibility into the underlay, you could actually perform this function in the Open vSwitch and not rely on the top of rack, which actually has a number of advantages. Open vSwitch can do a lot more policies than your typical top of rack switch. There are a number of additional use cases. I'm not going to go through all of them. But they all sort of have the same sort of theme, that what you're looking for are various overloaded resources within your infrastructure. And then you want to be able to have enough detail to understand what demand is driving utilization of that resource, trace it back to its source, and then apply some kind of control. So it might be a denial of service attack. Your control is to drop the traffic. It might be a load balancing decision. You can remark traffic. You could provision an optical circuit. You could move virtual machines to take, if they talk heavily together, remove that traffic from the physical network. You're doing network service chaining. You want to make sure that there's enough bandwidth available in the proposed path that you're going to create. And so the analytics gives you that visibility. And so my final comments are really that Open vSwitch is a part of a much bigger ecosystem, and that combining analytics from the physical and virtual infrastructure gives you the end-to-end visibility that's needed to really deliver on the performance that you'd want from any kind of virtualized service. And that finally, measurement feedback is the key to going beyond just provisioning cloud infrastructure, but really driving efficiency and optimal performance. So.
Let's thank our speaker. So we do have time for questions, so step up to a mic if you'd like to ask something of Peter. So it seems to me like this would be a pretty powerful combination with the tool that we saw presented previously if you were trying to troubleshoot some sort of problem in your network.
Yeah, I mean, SFlow is really about volumetric analysis. Mm-hmm. And so it's very good at seeing what's overutilized, what the hotspots are, what the large flows are. But it's not really a technology for doing tracing and troubleshooting. Mm-hmm. So tools like the one previously that gives you configuration checking, and also tracing tools. So if you're using Genev to mark and trace particular flows that just aren't working, those kinds of capabilities are very complementary to this kind of tool, which is saying, okay, everything's working, but I want to make it work better. and it's about resource management.
So you and InMon have contributed and have been maintaining the SFlow implementation in OVS since the beginning. Do you have plans for new enhancements over the next year?
Yeah, I mean, I think it'd be kind of interesting to see whether there's maybe some OVN metrics that might be worth pushing out. And then we're also looking at maybe doing more with the MPLS capabilities as well.
Okay. Yeah, the MPLS capabilities in OVS themselves need, there's a lot of opportunity for improvement there. So we'll look, I look forward to someone working on that as well. Looks like we have a question here.
Yes,
Yuri.
so I would like to ask how you relate those, or how you decide which line should you draw where in the diagram? Is it pre-configured statically or manually, or is there something more clever behind that?
Oh no, that diagram was statically drawn.
Yeah.
The general assumption is that when you build a leaf and spine fabric, that you a priori know what the topology is. They're highly structured networks, and any deviation from the design topology is a fault. So in deploying the system, you should know the topology, and then what you're doing is really mapping traffic into that a priori known topology. For the OVN side, we were actually pulling the metadata from the northbound API. So there you get the mapping between MAC addresses and logical switches. And So between the two, they meet in the middle. I mean, the basic idea with SFlow is that each entity is completely autonomous, but it annotates the measurements that it sends with enough metadata that you can join it. So when you export server metrics, the SFlow agent's a little unusual in that it actually exports the MAC address along with the metrics, which allows you to then join it to the network data. And the same sort of thing when we're looking at containers as well.
The question is very basic, and if it doesn't make much sense, please say so. But Bob Lance gave a talk earlier today on Mininet, and
Yes.
in performance modeling of the Mininet, he was talking about one of the capabilities he was talking about was reducing bandwidth.
Yeah.
So let's just say you had a NIC, and you have a virtual NIC, and you have the decision to throttle the bandwidth, and you reduce the bandwidth coming out from a particular virtual interface. In your diagrams that you showed, where would you see that particular measurement?
Well, that's actually one of the enhancements that somebody mentioned, was to have Open vSwitch more accurately report on IF speeds. So if you were actually throttling an interface using QDisk or something, it'd be nice to actually report the actual bandwidth available on that interface. And then you would, SFlow does export IF speeds along with the data, with the counter data that it's exporting for interfaces. So that would just transparently appear where to be properly set in the interface. But the other thing I'd like to really call out as a shout out here is that we use Mininet to simulate the system and provide the performance characteristics. So you can sort of set Mininet links to, say, to be 10 megabit links. And so we were basically scaling down this 10 gigabit network to a 10 megabit network, but we simulated this entire system and then deployed at 10 gig, and the results were identical. So it was a very faithful representation of the ultimate target system that we were deploying.
I have a small question. And you are going to support the OVS DPDK? The reason is so OVS DPDK used the Phaal mode driver, and the metric, OVS metric was, so CPU load is always 100% is used,
Well,
even though no packet is coming.
Well, it's 100% used. I mean, you've burnt a CPU. So as a resource management problem, I think that's the correct representation, because it's a CPU can't run a VM or anything else. So it runs busy.
We have time for another question if anyone has one. It doesn't look like it, so let's thank our speaker once more.
Thank you.